Our universe is a strange and wondrous place. At the grandest scales, we see galaxies colliding, stars exploding, and black holes warping the fabric of space-time. But what about the smallest scales? What happens when we zoom in on the universe, past atoms, past protons and neutrons, to the very building blocks of reality?
This is the domain of quantum mechanics, a realm where the rules of classical physics break down and the universe reveals its most baffling secrets. In the quantum world, particles don't behave like tiny billiard balls. Instead, they act like waves, spread out over space, existing in multiple states at once. They can tunnel through walls, instantly communicate over vast distances, and even seem to defy the flow of time.
Our intuition, honed by years of experience in the macroscopic world, fails us completely in this strange new landscape. This is a world where certainty dissolves into probability, where the act of observation can alter the very fabric of reality. It's a world that challenges our deepest assumptions about the nature of existence, forcing us to confront the possibility that our universe is far stranger and more wondrous than we ever imagined.
The story of quantum mechanics is a story of revolution, a paradigm shift that shattered the deterministic worldview of classical physics. It began in the early 20th century, a time of great intellectual ferment, when physicists were grappling with unexplained phenomena that defied the established laws of nature.
Classical physics, with its elegant equations and predictable outcomes, seemed incapable of explaining the strange behavior of light and matter at the atomic level. It couldn't account for the discrete energy levels of atoms, the wave-particle duality of light, or the bizarre properties of radioactive decay. A new framework was needed, one that could make sense of this emerging quantum reality.
Pioneers like Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrodinger rose to the challenge. They developed a radical new theory, quantum mechanics, that embraced uncertainty and probability as fundamental aspects of the universe. They showed that at the atomic and subatomic levels, particles exist in a superposition of states, a hazy cloud of possibilities rather than definite points in space and time.
This quantum revolution was not without its detractors. Even Albert Einstein, one of the founders of quantum theory, famously resisted its implications, declaring that God does not play dice with the universe. But the experimental evidence was undeniable. Quantum mechanics worked, accurately predicting the behavior of particles and atoms with unprecedented precision.
One of the most challenging aspects of quantum mechanics is that it defies our everyday intuition. In the quantum realm, classical notions break down.
Take, for example, wave-particle duality. Particles like electrons and photons can exhibit both wave-like and particle-like behavior.
Then there's quantum entanglement. When two particles become entangled, their fates become intertwined, no matter how far apart they may be. Quantum mechanics is often described as weird, counterintuitive, and even downright bizarre, and for good reason. It challenges our deeply ingrained assumptions about how the world works, forcing us to confront the possibility that reality itself is far stranger than we ever imagined.
But within this strangeness lies a profound beauty, a glimpse into the elegant and intricate workings of the universe at its most fundamental level. At the heart of quantum weirdness lies the concept of uncertainty. Unlike classical physics, which assumes that the properties of objects can be known with absolute certainty, quantum mechanics embraces uncertainty as a fundamental aspect of nature.
This isn't just a matter of our limited ability to measure things accurately. It's woven into the very fabric of reality. This embrace of uncertainty is not a sign of weakness or incompleteness in the theory. On the contrary, it's a testament to the depth and subtlety of quantum mechanics.
It reflects the fact that at the atomic and subatomic levels, the universe is not a collection of discrete objects with well-defined properties, but a dynamic web of interconnected possibilities. In this quantum realm, particles don't exist in definite states until they are observed. Instead, they exist in a superposition of states, a ghostly blend of all possible outcomes. It's only when we make a measurement, when we interact with the quantum system, that the wave function collapses and the particle chooses a particular state.
The double-slit experiment is a famous demonstration of wave-particle duality. First performed with light in the early 19th century, it reveals the strangeness of quantum mechanics.
Imagine a beam of light shining on a barrier with two narrow slits. Behind the barrier is a screen that records where the light hits. We'd expect to see two bright bands if light were particles.
But with many photons, an interference pattern appears, like waves. This pattern shows photons behaving like waves, interfering with themselves.
Observing which slit photons pass through collapses the wave function. The act of observation forces photons to behave like particles.
The concept of superposition lies at the heart of quantum mechanics. A quantum system can exist in multiple states simultaneously.
Like a coin spinning, both heads and tails at the same time. The system genuinely exists in a superposition of all possible states.
Imagine a single electron orbiting the nucleus of an atom. In the quantum world, the electron doesn't follow a single path. It exists in a superposition of all possible paths, a cloud of probability. Section 5, Schrödinger's cat, a thought experiment in quantum paradox. One of the most famous illustrations of superposition, and one that highlights its seemingly bizarre implications, is the thought experiment known as Schrödinger's cat.
This thought experiment, devised by physicist Erwin Schrödinger in 1935, uses a macroscopic object, a cat, to illustrate the strangeness of quantum superposition. Imagine a cat sealed inside a box along with a device that has a 50% chance of releasing a lethal poison. The device is triggered by a quantum event, such as the decay of a radioactive atom. According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of states, both alive and dead.
It's only when we make the observation that the wave function collapses and the cat chooses one state or the other. This thought experiment highlights the seemingly absurd implications of superposition when applied to the macroscopic world. It's one thing to say that an electron exists in a superposition of states, but it's quite another to imagine a cat being both alive and dead at the same time.
Schrödinger's cat is, of course, a thought experiment, not a real experiment. It's designed to highlight the strangeness of quantum mechanics and the challenges it poses to our intuitive understanding of reality. It forces us to confront the possibility that the act of observation plays a crucial role in shaping the world around us.
Section 6. Quantum entanglement. The spooky link between distant particles. Perhaps the most mind-boggling and counterintuitive phenomenon in quantum mechanics is quantum entanglement.
This strange link between distant particles, which even Einstein found deeply unsettling, suggests a level of interconnectedness in the universe that defies our classical understanding of space and time. Imagine two particles that have interacted in a way that links their fates no matter how far apart they may be. These particles are said to be entangled.
Now imagine separating these entangled particles, placing them at opposite ends of the universe. According to quantum mechanics, if you measure the state of one particle, you instantaneously determine the state of the other particle, even though they are light years apart.
This instantaneous correlation between entangled particles seems to violate the principle of locality, which states that objects can only be influenced by their immediate surroundings. It suggests that information can travel faster than the speed of light, a concept that contradicts Einstein's theory of special relativity.
Einstein famously called entanglement spooky action at a distance because he found the implications so unsettling. He believed that there must be some hidden variables, some unknown factors, that explained this seemingly instantaneous connection. However, decades of experiments have confirmed the reality of entanglement, showing that the correlation between entangled particles is real and that it cannot be explained by any classical theory. Section 1, the dawn of quantum mechanics, a revolution in physics. The early 20th century was a time of great intellectual ferment in the world of physics. Classical physics, the elegant and deterministic framework that had reigned supreme for centuries, was facing a crisis.
New experimental observations, particularly in the realm of atomic and subatomic physics, were revealing phenomena that simply could not be explained by the established laws of nature. These were not minor discrepancies. easily brushed aside as experimental error or theoretical oversights. They were fundamental challenges to the very foundations of classical physics, cracks in the edifice that threatened to bring the whole structure crashing down.
The universe, it seemed, was far stranger and more wondrous than anyone had imagined. It was against this backdrop of intellectual upheaval that a new theory emerged, a theory that would revolutionize our understanding of the universe and our place within it.
This theory, quantum mechanics, was not the work of a single brilliant mind, but rather the culmination of decades of research and collaboration by some of the greatest physicists of the 20th century. From Max Planck's groundbreaking work on blackbody radiation to Albert Einstein's explanation of the photoelectric effect to Niels Bohr's revolutionary model of the atom, the development of quantum mechanics was a story of intellectual daring, experimental ingenuity, and a willingness to embrace the unknown. Section 2. Max Planck and the Quantum Hypothesis, the Seeds of Revolution.
The seeds of the quantum revolution were sown in the year 1900 by a German physicist named Max Planck. Planck was studying a seemingly mundane problem: the spectrum of light emitted by a heated object known as blackbody radiation.
Classical physics predicted that the intensity of this radiation should increase infinitely as the frequency of the light increased, a prediction that clearly contradicted experimental observations. Planck struggled for months to reconcile theory with experiment, trying every trick in the classical physics playbook.
Finally, in an act of desperation, he introduced a radical new idea: that energy, instead of being continuous and infinitely divisible, as classical physics assumed, was actually quantized, meaning it could only exist in discrete packets, or quanta.
This quantum hypothesis, as it came to be known, was a radical departure from classical physics. It implied that energy, like matter, was not smooth and continuous, but rather grainy and discrete, like tiny bundles of energy. Planck himself was hesitant to embrace the full implications of his own hypothesis, viewing it more as a mathematical trick than a fundamental description of reality.
However, the quantum hypothesis proved remarkably successful in explaining the spectrum of blackbody radiation, accurately predicting the experimental observations that had stumped classical physics. Planck's work, for which he was awarded the Nobel Prize in Physics in 1918, marked the birth of quantum mechanics and ushered in a new era in our understanding of the universe.
Section 3. Einstein and the photoelectric effect, light as particles.
5 years after Max Planck introduced the quantum hypothesis, Albert Einstein took the next revolutionary step. He studied the photoelectric effect, where light causes electrons to be emitted from metal.
Classical physics predicted electron energy depended on light intensity, but experiments showed it depended only on light frequency.
Einstein proposed light is quantized into photons. Each photon's energy is proportional to its frequency. This explained the photoelectric effect and earned Einstein the Nobel Prize in 1921.
Section 4. Niels Bohr's atomic model, quantizing the atom.
In 1913, Niels Bohr proposed a revolutionary new model of the atom. The Rutherford model depicted the atom as a miniature solar system.
But it predicted electrons would spiral into the nucleus.
Bohr proposed that electrons occupy discrete energy levels. These orbits were quantized with specific allowed energies.
Electrons emit photons when transitioning between energy levels.
Bohr's model explained the hydrogen emission spectrum. It introduced quantum jumps central to atomic behavior. Werner Heisenberg and the uncertainty principle, embracing the unknown. As the 1920s progressed, quantum mechanics evolved rapidly.
Heisenberg's uncertainty principle, formulated in 1927, states fundamental limits to the precision of certain pairs of physical properties.
The more precisely we know a particle's position, the less precisely we know its momentum. This is an inherent property of the quantum world.
The uncertainty principle implies a fundamental fuzziness to reality. Particles exist as a cloud of probability, their properties smeared over a range of values.
Section 6. Erwin Schrodinger and wave mechanics, describing the quantum world. In 1926, Austrian physicist Erwin Schrodinger made a groundbreaking contribution to quantum mechanics by developing a mathematical framework known as wave mechanics.
Schrödinger's wave mechanics provided a powerful new way to describe the behavior of quantum systems, complementing the matrix mechanics developed earlier by Werner Heisenberg. Schrödinger's key insight was to describe the state of a quantum system using a mathematical function called a wave function.
The wave function, denoted by the Greek letter ESI, psi, contains all the information about the system, including its energy, momentum, and position. However, unlike classical physics, where these properties have definite values, in quantum mechanics they are represented by probabilities.
The square of the absolute value of the wave function at a particular point in space gives the probability of finding the particle at that point. Thus, the wave function describes a particle as a wave of probability spread out over space rather than as a point-like object with a definite location.
This wave-like nature of quantum particles, as captured by Schrödinger's wave mechanics, explains phenomena such as wave-particle duality and quantum tunneling. Schrödinger's wave mechanics, though initially met with skepticism from some physicists who questioned the physical interpretation of the wave function, proved to be a powerful tool for solving quantum mechanical problems.
It provided a unified framework for understanding a wide range of quantum phenomena, from the behavior of atoms and molecules to the properties of solids and liquids.
Section 7. The Copenhagen interpretation, making sense of the quantum world. As the 1920s drew to a close, quantum mechanics had emerged as a powerful and successful theory.
The interpretation of quantum mechanics remained a subject of intense debate. The Copenhagen interpretation emerged, named after the city where Niels Bohr and Werner Heisenberg worked.
It rests on several key principles: quantum superposition, wave function collapse, the observer effect, complementarity, and statistical interpretation. Despite criticisms, it has provided a consistent framework for understanding quantum mechanics, leading to countless technological advances and deepening our understanding of the universe.
From revolution to revelation, the enduring impact of quantum mechanics. The development of quantum mechanics in the early 20th century was nothing short of a revolution in physics, shattering the deterministic worldview of classical physics and revealing a universe far stranger and more wondrous than anyone had imagined.
From the quantization of energy and light to the wave-particle duality of matter to the uncertainty principle and the observer effect, quantum mechanics has challenged our most fundamental assumptions about the nature of reality.
Yet, quantum mechanics is more than just a revolution in physics. It is a revelation about the nature of the universe and our place within it. It has shown us that the universe is inherently uncertain, that particles exist as waves of probability, and that the act of observation plays a crucial role in shaping reality.
The impact of quantum mechanics extends far beyond the realm of theoretical physics. It has led to countless technological advances, from transistors and lasers to medical imaging and nuclear energy.
It underpins our understanding of chemistry, biology, and material science, and it continues to inspire new generations of physicists, mathematicians, and philosophers as they grapple with its profound implications.
Quantum mechanics has taught us to embrace the unknown, to accept that the universe is far stranger and more wondrous than we ever imagined. It has shown us that reality is not a fixed and immutable thing, but rather a dynamic and ever-evolving tapestry woven from the threads of probability, uncertainty, and observation. The quantum observer shaping reality through observation. The role of the observer in quantum mechanics is profound. In classical physics, objects exist independently of observation.
Events unfold regardless of observation. In quantum mechanics, observation shapes reality.
The universe exists as possibilities until observed. A single electron exists as a wave of probability.
Measurement collapses this wave to a definite position. Observation alters the state of a quantum system.
This is a radical departure from classical physics. Does consciousness create reality? The measurement problem. The role of the observer in quantum mechanics raises a host of profound and often unsettling questions. If the act of observation can collapse the wave function and force a quantum system into a definite state, does that mean that consciousness itself plays a role in shaping reality?
Is the universe, as some have suggested, a kind of cosmic mind, with our observations serving as the thoughts that bring it into being? This question of whether consciousness creates reality is often referred to as the measurement problem, and it has been a subject of intense debate among physicists and philosophers for nearly a century.
Some argue that consciousness is indeed a fundamental aspect of reality, and that the act of observation is what collapses the wave function and brings the universe into existence.
Others maintain that consciousness is an emergent property of complex systems, like the human brain, and that it plays no fundamental role in quantum mechanics.
The measurement problem highlights the deep philosophical implications of quantum mechanics. It forces us to confront the possibility that our understanding of reality is fundamentally incomplete, that there may be levels of existence beyond our current comprehension.
It challenges us to rethink our place in the cosmos, to consider the possibility that we are not merely passive observers of the universe, but active participants in its unfolding drama. At the heart of the measurement problem lies the enigmatic process of wave function collapse. Imagine a quantum system, such as an electron, existing in a superposition of states, a ghostly blend of all possible outcomes.
Before a measurement is made, the electron doesn't have a definite position, momentum, or energy. It exists as a wave of probability, spread out over a region of space. The wave function, a mathematical function that describes the state of a quantum system, encapsulates this superposition of possibilities.
It doesn't tell us where the electron is, but rather provides a set of probabilities for finding it at various locations. The act of measurement, of interacting with the electron in a way that forces it to reveal its position, causes this wave function to collapse.
The electron, once spread out over a range of possibilities, suddenly snaps into a definite state, a single point in space. This collapse of the wave function is what gives rise to the classical world we experience, a world of definite objects with well-defined properties.
But it also raises a host of perplexing questions. What constitutes a measurement? Does it require a conscious observer? Or can a measuring device, such as a detector, also collapse the wave function? And what happens to all the other possibilities, the other outcomes that were encoded in the wave function before it collapsed? Schrödinger's cat, that enduring thought experiment in quantum paradox, provides a vivid illustration of the measurement problem and the collapse of the wave function. Recall the setup. A cat is sealed inside a box, along with a device that has a 50% chance of releasing a lethal poison.
The trigger for this device is a quantum event, such as the decay of a radioactive atom. According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of states, both alive and dead. The cat's fate is entangled with the state of the radioactive atom, which itself exists in a superposition of decayed and undecayed states.
It's only when we make the observation, when we open the box and look inside, that the wave function collapses and the cat chooses one state or the other, alive or dead. Schrödinger's cat highlights the seemingly absurd implications of applying quantum mechanics to macroscopic objects.
It's one thing to say that an electron exists in a superposition of states, but it's quite another to imagine a cat being both alive and dead at the same time. The thought experiment forces us to confront the question of where the boundary lies between the quantum world, where superposition reigns supreme, and the classical world, where objects have definite properties. The many worlds. Interpretation, a mind-bending alternative to the Copenhagen interpretation, offers a radical solution to the measurement problem and the collapse of the wave function. Proposed by physicist Hugh Everett III in 1957, the MWI suggests that wave function collapse is an illusion, and that all possible outcomes of a quantum measurement actually occur, but in different, non-interacting universes.
According to the MWI, every time a quantum measurement is made, the universe splits, creating a new universe for each possible outcome. In the case of Schrödinger's cat, for example, there would be one universe where the cat is alive and another universe where the cat is dead.
These universes, once separated, continue to evolve independently of each other, their inhabitants forever unaware of their counterparts in other branches of reality. The MWI, though highly speculative, has gained increasing acceptance among some physicists and cosmologists.
It offers an elegant and deterministic solution to the measurement problem, eliminating the need for wave function collapse or any special role for the observer. However, it also raises a host of profound philosophical questions about the nature of identity, free will, and the meaning of existence in a multiverse of infinite possibilities. Can we ever know the true nature of reality, the limits of observation? The observer effect and the measurement problem highlight a fundamental limitation to our understanding of the universe. In the quantum realm, the very act of observation, of interacting with a system to gain information about it, inevitably alters the state of that system. This raises the unsettling possibility that we can never truly know the objective, observer-independent nature of reality. Imagine trying to observe a delicate soap bubble without disturbing it. No matter how carefully you approach it, no matter how gently you try to illuminate it, your very presence will inevitably alter its shape, its color, its very existence. The same is true, in a sense, for the quantum world. Our attempts to observe it, to pin it down and force it to reveal its secrets, inevitably alter the very reality we seek to understand. This doesn't mean that science is futile or that our pursuit of knowledge is in vain. On the contrary, it highlights the profound and humbling nature of the scientific endeavor. We are not detached observers standing outside the universe, objectively measuring its properties. We are participants in the cosmic dance, our observations shaping the very reality we seek to understand. The quantum observer and the future, the unfolding tapestry of reality. As we delve deeper into the mysteries of the quantum world, the role of the observer will continue to challenge our assumptions and shape our understanding of reality. The observer effect and the measurement problem are not merely esoteric puzzles for physicists and philosophers to ponder. They have profound implications for the future of science and technology. Quantum computing, for example, which harnesses the bizarre properties of superposition and entanglement to perform calculations that are impossible for classical computers, relies on our ability to control and manipulate quantum systems at the level of individual particles. The observer effect, far from being a nuisance, is an essential ingredient in these technologies, allowing us to manipulate the very fabric of reality to achieve unprecedented computational power. Similarly, quantum cryptography, which leverages the principles of quantum mechanics to create unbreakable encryption schemes, relies on the observer effect to ensure the security of communications. Any attempt to eavesdrop on a quantum communication channel would inevitably disturb the system, alerting the intended recipients to the presence of an intruder. Beyond the observer, exploring the deeper implications of quantum mechanics. The role of the observer in quantum mechanics is just one facet of a profound and multifaceted theory that continues to challenge our understanding of the universe. As we continue to explore the implications of quantum mechanics, we are likely to encounter even stranger and more wondrous phenomena, pushing the boundaries of our imagination and forcing us to confront the limits of our current worldview. One area of active research is quantum gravity, the quest to unify quantum mechanics with Einstein's theory of general relativity, which describes the force of gravity. This unification, if achieved, could provide profound new insights into the nature of space, time, and the origins of the universe. It might even shed light on the mysteries of dark matter and dark energy, the invisible forces that seem to govern the evolution of the cosmos. Another area of exploration is the connection between quantum mechanics and consciousness. While the measurement problem remains unresolved, the possibility that consciousness plays a fundamental role in shaping reality continues to intrigue physicists, philosophers, and neuroscientists alike. Further research in this area could have profound implications for our understanding of ourselves and our place in the universe.
Quantum mechanics, for all its strangeness and counterintuitive implications, is far from being an abstract and esoteric theory confined to the ivory towers of academia. On the contrary, it underpins much of the technology that powers our modern world, from smartphones and computers to lasers and medical imaging devices.
The quantum revolution, which began in the early 20th century, has quietly transformed our lives in countless ways, shaping the very fabric of our technological civilization. It's easy to overlook the profound impact of quantum mechanics on our daily lives.
We take for granted the devices that allow us to communicate instantly across vast distances, to access a world of information at our fingertips, to diagnose and treat diseases with unprecedented precision. Yet, none of these technologies would be possible without the insights into the nature of matter and energy provided by quantum mechanics.
The transistors that power our computers and smartphones, the lasers that read our Blu-ray discs and enable fiber optic communication, the magnetic resonance imaging machines that allow doctors to peer inside the human body, all of these technologies rely on the principles of quantum mechanics.
The quantum revolution, far from being a purely theoretical affair, has had a profound and tangible impact on our world, shaping the way we live, work, and interact with each other. At the heart of the digital revolution lies a tiny device called the transistor, a semiconductor device that can amplify or switch electronic signals and electrical power.
Invented in 1947 at Bell Laboratories, the transistor quickly revolutionized the world of electronics, replacing bulky and inefficient vacuum tubes and paving the way for the development of integrated circuits, microprocessors, and ultimately, the computers and smartphones we rely on today.
The transistor's operation is based on the principles of quantum mechanics, specifically the behavior of electrons in semiconductors. Semiconductors are materials that have electrical conductivity between that of a conductor like copper and an insulator like glass. Their conductivity can be controlled by adding impurities known as dopants, which introduce either extra electrons or holes where electrons are missing.
In a transistor, the flow of electrons through a semiconductor channel is controlled by an electric field applied to a gate electrode. The gate electrode, separated from the channel by a thin insulating layer, acts like a valve, regulating the flow of electrons from the source to the drain. This control over the flow of electrons allows the transistor to amplify signals or switch them on and off, forming the basis for digital logic circuits.
Lasers, those ubiquitous beams of highly focused monochromatic light, have become indispensable tools in a wide range of applications, from telecommunications and barcode scanners to laser surgery and cutting-edge scientific research.
The invention of the laser in 1960 was a triumph of quantum mechanics, harnessing the principles of stimulated emission and quantized energy levels to create a beam of light with unprecedented properties. Unlike ordinary light sources, which emit light in a wide range of frequencies and directions, lasers produce light that is both monochromatic and coherent.
These properties arise from the quantum nature of light and the interaction of light with matter. In a laser, atoms or molecules within a gain medium, such as a crystal or gas, are excited to higher energy levels by an external energy source, such as a flash lamp or electrical discharge. When these excited atoms or molecules return to their ground state, they emit photons of light.
A key feature of lasers is stimulated emission, a process in which a photon passing by an excited atom or molecule can stimulate it to emit a second photon that is identical in frequency, phase, and direction to the first.
Medical imaging has revolutionized the diagnosis and treatment of diseases, allowing doctors to peer inside the human body without invasive surgery. Many of these imaging techniques, such as magnetic resonance imaging, positron emission tomography, and computed tomography scans, rely on the principles of quantum mechanics to create detailed images of our internal organs and tissues.
MRI, one of the most widely used medical imaging techniques, exploits the quantum mechanical properties of atomic nuclei, specifically their spin-angular momentum. Atomic nuclei, like tiny spinning tops, possess a magnetic moment, a measure of their tendency to align with a magnetic field.
In an MRI machine, a strong magnetic field aligns the spins of atomic nuclei within the body. Radio waves are then used to temporarily perturb these spins, causing them to emit radio signals that are detected by the MRI machine.
By analyzing the strength and frequency of these emitted radio signals, the MRI machine can create detailed images of the body's tissues and organs, distinguishing between different types of tissues based on their water content, blood flow, and other properties. MRI is particularly useful for imaging soft tissues, such as the brain, spinal cord, and muscles, providing valuable information for diagnosing a wide range of conditions, from tumors and strokes to ligament tears and spinal cord injuries.
Quantum computing, a revolutionary new paradigm for processing information, harnesses the bizarre properties of quantum mechanics to perform calculations that are impossible for even the most powerful classical computers. While still in its early stages of development, quantum computing has the potential to revolutionize fields as diverse as medicine, materials, science, artificial intelligence, and cryptography.
Classical computers, like the ones we use every day, store and process information in bits, which can represent either a 0 or a 1. Quantum computers, on the other hand, utilize quantum bits or qubits. A qubit, unlike a classical bit, can exist in a superposition of states, simultaneously representing both a 0 and a 1. This property of superposition, along with quantum entanglement, allows quantum computers to perform computations in a fundamentally different way than classical computers.
Imagine trying to find a specific grain of sand on a vast beach. A classical computer would have to search each grain of sand one by one until it found the right one. A quantum computer, on the other hand, could examine all the grains of sand simultaneously, thanks to superposition dramatically speeding up the search. While quantum computers are still in their infancy, their potential impact on various fields is immense.
In medicine, quantum computers could revolutionize drug discovery by simulating the interactions of molecules with unprecedented accuracy, leading to the development of new drugs and therapies for diseases that are currently incurable. They could also enable personalized medicine, tailoring treatments to an individual's unique genetic makeup.
In materials science, quantum computers could help design new materials with superior properties, such as lighter and stronger alloys for aircraft or more efficient solar cells for renewable energy. They could also accelerate the development of high-temperature superconductors, materials that conduct electricity with zero resistance, revolutionizing energy transmission and storage.
Artificial intelligence stands to benefit greatly from quantum computing. Quantum computers could accelerate machine learning algorithms, enabling AI systems to learn from data much faster and solve complex problems that are currently intractable for classical computers. This could lead to breakthroughs in areas such as natural language processing, image recognition, and autonomous driving.
Section 7. Quantum cryptography, unbreakable codes for a quantum age. In an age of increasing reliance on digital communication and data storage, the security of information is paramount.
Quantum cryptography, a field that leverages the principles of quantum mechanics to create unbreakable encryption schemes, offers a new level of security for our digital world.
Classical cryptography, the foundation of online security protocols, relies on mathematical algorithms that are difficult but not impossible for classical computers to break. As computers become more powerful, the security of these encryption schemes becomes increasingly vulnerable.
Quantum computers, with their ability to factor large numbers exponentially faster than classical computers, pose a significant threat to classical cryptography.
Quantum cryptography, in contrast, exploits the fundamental properties of quantum mechanics, such as the observer effect and the no-cloning theorem, to create encryption keys that are impossible to eavesdrop on without detection.
The observer effect dictates that any attempt to measure a quantum system inevitably alters its state. The no-cloning theorem states that it is impossible to create an exact copy of an unknown quantum state.
Section 8. Quantum biology, life's quantum secrets. Quantum mechanics, once thought to be relevant only to the realm of inanimate matter, is now being explored as a key player in the intricate dance of life itself.
Quantum biology, an emerging field at the intersection of physics and biology, seeks to understand how quantum phenomena, such as superposition, entanglement, and tunneling, might play a role in biological processes.
One area of active research is photosynthesis, the process by which plants, algae, and some bacteria convert sunlight into chemical energy. Recent studies suggest that quantum coherence, a phenomenon in which multiple quantum states can exist simultaneously, might play a role in the efficient transfer of energy during photosynthesis.
This discovery could have implications for the development of artificial photosynthesis systems for renewable energy production.
Another intriguing area of research is olfaction, our sense of smell. The prevailing theory of olfaction suggests that molecules bind to receptors in our noses, triggering a signal that our brains interpret as a specific odor.
However, some scientists propose that quantum tunneling, a phenomenon in which particles can pass through energy barriers that classical physics deems insurmountable, might play a role in allowing odorant molecules to interact with receptors.
Section 9. The Quantum Future, a world transformed by quantum technology. The quantum revolution, which began in the early 20th century as a series of perplexing experimental results and theoretical breakthroughs, is poised to transform the 21st century in profound and unpredictable ways.
Quantum technologies, once confined to research labs and the realm of science fiction, are rapidly moving into the mainstream, promising to revolutionize fields as diverse as medicine, computing, communication, and energy production.
Quantum computers, with their ability to perform calculations that are impossible for classical computers, have the potential to solve some of humanity's most pressing challenges, from developing new drugs and therapies for diseases to designing new materials for renewable energy and tackling climate change.
Quantum communication networks, leveraging the principles of quantum entanglement, could enable ultra-secure communication channels, impervious to eavesdropping, ushering in a new era of privacy and security in the digital age.
Quantum sensors, with their unparalleled sensitivity, could revolutionize fields such as medical diagnostics, environmental monitoring, and materials testing, enabling us to detect and measure phenomena with unprecedented precision.
Quantum metrology, the science of making ultra-precise measurements, could lead to the development of new standards and technologies that underpin our understanding of the fundamental constants of nature.
The quantum future is full of both promise and uncertainty. As we delve deeper into the mysteries of the quantum world, we are likely to encounter even stranger and more wondrous phenomena, challenging our assumptions and pushing the boundaries of our imagination. Interpreting the quantum enigma, a tapestry of perspectives. Quantum mechanics, for all its triumphs in explaining the behavior of matter and energy at the atomic and subatomic levels, has left physicists with a profound and enduring puzzle, the interpretation of the theory itself.
While the mathematical framework of quantum mechanics is remarkably successful in predicting experimental outcomes, the question of what it actually means about the nature of reality remains a subject of intense debate and speculation.
Unlike classical physics, which offers a clear and intuitive picture of the world as a collection of objects with well-defined properties, quantum mechanics presents a far stranger and more counterintuitive view.
The concepts of superposition, wave function collapse, and the observer effect, while essential to the theory's predictive power, challenge our deeply ingrained assumptions about how the world works.
Over the decades, physicists and philosophers have proposed a wide range of interpretations of quantum mechanics, each attempting to provide a coherent and consistent explanation for the theory's bizarre predictions.
These interpretations, while often differing in their metaphysical assumptions and philosophical implications, all strive to make sense of the quantum enigma, to reconcile the strangeness of the quantum world with our everyday experience of a classical reality.
The Copenhagen interpretation, named after the city where many of its key proponents, including Niels Bohr and Werner Heisenberg, worked, has emerged as the most widely accepted interpretation of quantum mechanics.
It is a testament to the theory's profound strangeness that the interpretation most widely embraced by physicists is one that, in many ways, sidesteps the question of what quantum mechanics actually means about the nature of reality.
Rather than attempting to provide a realist interpretation of the quantum formalism, the Copenhagen interpretation adopts a more pragmatic approach, focusing on the theory's predictive power and its ability to account for experimental observations.
It emphasizes the role of the observer in defining reality, suggesting that the act of measurement forces a quantum system into a definite state, collapsing the wave function and bringing about a classical outcome.
While the Copenhagen interpretation has been remarkably successful in guiding the development and application of quantum mechanics, it has also been criticized for its ambiguity and its seemingly subjective elements.
The concept of wave function collapse, while essential to the interpretation, remains poorly defined, leaving open the question of what constitutes a measurement and what role, if any, consciousness plays in the process.
The many worlds interpretation, MWI, proposed by physicist Hugh Everett III in 1957, offers a radical and mind-boggling alternative to the Copenhagen interpretation.
It suggests that the wave function collapse is an illusion, and that all possible outcomes of a quantum measurement actually occur, but in different, non-interacting universes.
According to the MWI, every time a quantum measurement is made, the universe splits, creating a new universe for each possible outcome.
These universes, once separated, continue to evolve independently of each other, their inhabitants forever unaware of their counterparts in other branches of reality.
In this view, the universe is not a single unique entity, but rather a vast and ever-expanding multiverse, encompassing an infinity of quantum realities.
The MWI, while highly speculative and lacking experimental confirmation, has gained increasing acceptance among some physicists and cosmologists.
It offers an elegant and deterministic solution to the measurement problem, eliminating the need for wave function collapse or any special role for the observer.
However, it also raises a host of profound philosophical questions about the nature of identity, free will, and the meaning of existence in a multiverse of infinite possibilities. Pilot wave theory, also known as de Broglie-Bohm theory, offers a distinct interpretation of quantum mechanics that seeks to restore determinism to the quantum world. Proposed by Louis de Broglie in the 1920s and later developed by David Bohm in the 1950s, pilot wave theory posits the existence of hidden variables not fully described by the standard quantum formalism that govern the behavior of quantum systems. In pilot wave theory, particles always have definite positions and momenta even when they are not being observed.
These particles are guided by a wave function known as the pilot wave, which determines their trajectories. The wave function evolves according to Schrödinger's equation, ensuring that the statistical predictions of quantum mechanics are preserved.
Pilot wave theory, while offering a deterministic and realist interpretation of quantum mechanics, has faced criticism for its non-locality. The idea that events in one region of space can instantaneously influence events in distant regions. It has also struggled to account for certain quantum phenomena, such as the spin of particles, in a fully satisfactory way. Objective collapse theories represent another attempt to resolve the measurement problem and provide a more realist interpretation of quantum mechanics. These theories propose that wave function collapse is a real physical process, independent of the observer, and that it occurs spontaneously or as a result of interactions with the environment.
One prominent objective collapse theory is the Girardi-Rimini-Weber (GRW) theory, which suggests that wave functions collapse spontaneously at random times, with the probability of collapse increasing with the size and complexity of the system. This spontaneous collapse mechanism ensures that microscopic systems remain in superposition, exhibiting quantum behavior, while macroscopic objects composed of a vast number of particles rapidly collapse to classical states.
Objective collapse theories, while offering a more objective and deterministic picture of quantum mechanics, face the challenge of explaining why we observe a sharp boundary between the quantum and classical worlds. They also require modifications to the standard quantum formalism, introducing new parameters and equations to describe the collapse process. The plethora of interpretations of quantum mechanics, each with its own strengths and weaknesses, highlights the profound challenge of making sense of the quantum world. While the Copenhagen interpretation has proven remarkably successful in guiding the development and application of quantum mechanics, its pragmatic approach leaves many fundamental questions unanswered.
The many worlds interpretation, with its mind-boggling multiverse, offers an elegant solution to the measurement problem, but at the cost of introducing a vast and untestable realm of parallel universes. Pilot wave theory attempts to restore determinism to the quantum world but struggles to account for certain quantum phenomena and introduces non-locality, a concept at odds with our intuitive understanding of space and time.
Objective collapse theories propose that wave function collapse is a real physical process, but face the challenge of explaining the quantum classical boundary and require modifications to the standard quantum formalism.
The search for a unified and compelling interpretation of quantum mechanics continues, driven by the desire to reconcile the theory's extraordinary predictive power with a coherent and consistent picture of reality. This quest has led physicists and philosophers to explore new avenues of thought, to question our most basic assumptions about the nature of the universe, and to embrace the possibility that the answers may lie beyond our current comprehension. Section 7. Beyond interpretation, the enduring legacy of quantum mechanics. The debate over the interpretation of quantum mechanics, while fascinating and philosophically profound, should not overshadow the theory's remarkable success in explaining the behavior of matter and energy at the atomic and subatomic levels.
Quantum mechanics has revolutionized our understanding of the universe, revealing a world far stranger and more wondrous than anyone had imagined. From the quantization of energy and light, to the wave-particle duality of matter, to the uncertainty principle and the observer effect, quantum mechanics has challenged our most fundamental assumptions about the nature of reality.
It has led to countless technological advances, from transistors and lasers to medical imaging and nuclear energy, transforming our world in profound and tangible ways.
The enduring legacy of quantum mechanics lies not only in its technological applications, but also in its profound impact on our understanding of the universe and our place within it. It has taught us to embrace the unknown, to accept that the universe is far stranger and more wondrous than we ever imagined.
It has shown us that reality is not a fixed and immutable thing, but rather a dynamic and ever-evolving tapestry woven from the threads of probability, uncertainty, and observation. The quest to understand quantum mechanics, to unravel its mysteries and reconcile its strangeness with our everyday experience, will undoubtedly continue for generations to come. Section 1. Quantum questions. Probing the nature of reality. Quantum mechanics, with its profound strangeness and counterintuitive implications, has not only revolutionized our understanding of the universe, but has also ignited a firestorm of philosophical debate and speculation.
The very nature of reality, the role of the observer, the meaning of time and causality, all these fundamental concepts, once thought to be the exclusive domain of philosophers, have been thrust into the spotlight by the bizarre findings of quantum mechanics.
The quantum world, it seems, operates by a different set of rules than the classical world we experience every day. Particles can exist in multiple states simultaneously, entangled across vast distances, their fates intertwined in ways that defy our classical notions of space and time.
The act of observation, far from being a passive process of simply revealing pre-existing properties, seems to play an active role in shaping the very reality we seek to understand.
These findings have forced physicists and philosophers alike to confront some of the deepest and most enduring questions about the nature of existence. Is reality objective, existing independently of our observations, or is it subjective, shaped by the act of measurement?
Does consciousness play a fundamental role in the universe, or is it merely an emergent property of complex systems? What does quantum mechanics tell us about the nature of time, causality, and the relationship between the observer and the observed?
Is reality objective, existing independently of our observations, or subjective, shaped by the act of measurement?
Classical physics assumes an objective reality, but quantum mechanics questions this.
The observer effect suggests that observation influences the state of a quantum system.
Does the universe choose its state only when we are watching? This has profound implications.
If reality is observer-dependent, our role in the universe becomes significant.
The idea of a subjective reality raises philosophical challenges, suggesting a kind of cosmic consciousness. The role of consciousness in quantum mechanics is perplexing and controversial.
Some speculate that consciousness might play a fundamental role in shaping reality.
Many physicists argue that consciousness is an emergent property and plays no fundamental role in physics.
Quantum systems interact without conscious observers, explaining their behavior.
The hard problem of consciousness remains one of science's biggest mysteries. The question of free will has vexed philosophers for centuries.
Quantum mechanics, with its emphasis on probability and uncertainty, offers challenges and potential solutions to free will.
Quantum mechanics seems to undermine the notion of a deterministic universe.
The uncertainty principle suggests inherent randomness in the universe.
This randomness could provide a loophole for free will.
However, some argue that quantum randomness does not equate to free will.
Time has long captivated physicists and philosophers.
Classical physics does not distinguish between forward and backward time.
Quantum mechanics introduces intriguing wrinkles into our understanding of time.
Wave function collapse suggests a preferred direction of time.
The wave function evolves deterministically, but collapses instantaneously upon measurement.
This collapse process is not time reversible.
Quantum mechanics might provide a clue to understanding the arrow of time.
Quantum entanglement challenges classical notions of causality.
The quest for a theory of everything aims to unify all fundamental forces of nature.
Quantum mechanics and general relativity are fundamentally incompatible.
This incompatibility hampers attempts to unify the two theories.
The search for a theory of everything continues, driven by the belief in a deeper, more fundamental theory.
Promising candidates include string theory and loop quantum gravity.
Quantum mechanics raises questions about the meaning of it all.
If reality is shaped by observation, what does it mean for us?
Some find a sense of awe and wonder in quantum mechanics.
The idea that we are active participants in shaping reality can be exhilarating and humbling.
It suggests a deep interconnectedness between ourselves and the universe.
Others find existential angst in the inherent randomness of the universe.
Quantum mechanics remains an unfinished symphony.
It has raised more questions than it has answered.
The interpretation of quantum mechanics and the role of consciousness are enduring mysteries.
The exploration of the quantum world is far from over.
New experimental techniques and theoretical breakthroughs are pushing the boundaries of our knowledge.
Quantum computing and quantum cryptography promise to revolutionize our world. The Quantum Legacy, a universe reimagined.
Quantum mechanics has revolutionized our understanding of the universe.
It has shattered the deterministic worldview of classical physics.
Quantum mechanics challenged our deepest intuitions about reality.
It has given us tools to understand the structure of atoms and the origins of the universe. The unanswered questions, mysteries yet to unfold.
Quantum mechanics remains an enigma.
The interpretation of the theory continues to spark debate.
The role of consciousness and the unification with general relativity are profound mysteries.
The many worlds interpretation challenges us to imagine a grander reality.
Each interpretation offers a unique perspective on the quantum enigma.
Quantum Horizons, exploring the frontiers of knowledge.
The quest to understand quantum mechanics has driven groundbreaking advancements.
Quantum technologies are rapidly moving into the mainstream.
Quantum computers hold the potential to solve humanity's most pressing challenges.
Quantum communication networks could enable ultra-secure communication channels.
Quantum sensors could revolutionize fields such as medical diagnostics and environmental monitoring.
The Quantum Symphony, a universe of wonder and possibility.
The exploration of the quantum realm has been transformative.
Quantum mechanics has shown us a reality far richer and stranger than we imagine.
the universe is a vibrant, interconnected tapestry.
The quantum symphony will continue to echo through science, philosophy, and the human